This week we are talking about cardinality of sets. Of course, here we are going to mainly deal with infinite sets because when it comes to finite sets, cardinality is trivial. So we are going to mainly focus our attention on the cardinality of infinite sets. And we will also talk about the Schroeder-Bernstein theorem that helps us to compare especially infinite sets in cardinality. And based on the cardinality of sets discussion, we are going to move on to counting because we will see types of infinity and then we will turn back to what is discrete and what is not. So the cardinality of sets discussion is going to help us to understand what is discrete and what is not. And based on this, we are going to come back to finite stuff and we'll talk about counting methods to determine the number of several properties of discrete structures. In this context, of course, we are going to talk about product and sum rules, which are quite basic and elementary, permutations and combinations again. And towards the end of this class, we are going to see some maybe advanced subjects such as representations that help us enumerate certain structures, the inclusion-exclusion principle, and the so-called object box problems. So let's start with cardinality of sets, and this is essentially based on functions. Cardinality of sets has a lot to do with functions that we can define from one set to another. And the main results are here. If there exists a one-to-one function from set A to set B, then the cardinality of set A is less than or equal to the cardinality of set B. And this is demonstrated here. You see, we have a function which is one-to-one from A to B, which means there are left out elements in B. Therefore, the cardinality of B must be greater than or equal to cardinality of A, because otherwise it would not be possible to define a one-to-one function. Why? Because if you have more elements here, let's say you have this one, this one, this one, which would make it equal. So let me set this as my one-to-one function, but if I have even just one more, now how am I going to map this one? There is no element available in B that is not mapped to. Therefore, it will not be possible to define a one-to-one function in this scenario. Let's look at the second one. If there exists an onto function from set A to set B, then the cardinality of A this time around must be greater than or equal to cardinality of B. And this is demonstrated here. Of course, if there is an onto function from A to B, this means there must be at least as many elements in A as in B, so that I can define an onto function. Otherwise, I cannot cover the entire set of B. Therefore, this should be the case. Now, when you combine these together, remember the definition of bijections. If a function is both one-to-one and onto, if you have such a function like this one, for instance, in this case, then the cardinality of these two sets are equal. Now, this one is going to be extremely important for us, and we are going to use this also when we talk about cardinality of infinite sets. Now, before moving on, I would like to make one more remark here. This also lays out the relationship between the cardinalities of sets and their subsets. So let's say A is a subset of B. In this case, obviously, it would be possible to define a one-to-one function from A to B, which could be the identity function, for instance, which means cardinality of A must be cardinality of B, which is not surprising, but you see we have a rigorous foundation for this result too. Now, as I said, we are going to focus on infinite sets in the context of cardinality because, of course, cardinality is trivial when you talk about finite sets. So what is um, interesting in this context is the cardinality of infinite sets. Earlier, we just said that this set is finite, this set is infinite, and that was the extent of our discussion with respect to cardinality. But you see, infinite sets, in terms of cardinality and many other stuff, they have peculiar properties. And one of them is the following. It is possible to define a bijection from an infinite set to at least one of its proper subsets. Now let's understand what this is saying. You have an infinite set and you have a proper subset of it, which means it's not the same set, so definitely you are missing some elements, at least one. So they are not the same sets. Some elements are missing in the subset so that it's a proper subset. The claim is it is possible to define a bijection between the two. Now, how could this be possible? Because we know that there are some elements missing. Now, let's see this on a real example here. Take the set as the set of points on this line segment AB, okay? And let's take the proper subset as CD, this one here, this line segment on AB. Clearly, CD is a proper subset because it's different than AB. Now, I'm going to define now this function. Let's translate this line segment CD to C prime D prime. Now, C prime D prime here, okay, this is parallel to CD. Okay, so it's parallel to the AB also, AB segment also. But what I'm doing is I'm going to connect A and C prime and B and D prime, and they, let's say, intersect at point P to form the triangle PAB. Now, take any point on line segment AB, let's say T. Okay, it doesn't have to be to the left of C, doesn't have to be to the right of D, doesn't have to be on CD, it could be anywhere at all on AB. Now take this point and connect it to point P and mark the point where it intersects with C prime D prime and call this T prime. Now connect T prime, okay, with an orthogonal to AB, and clearly it's going to fall onto CD, okay, and it's going to mark a point on CD, which is in this case the point S. Okay, so this is my function. I have this point T on AB, and then through this procedure, I map it to a point on CD. Now, it should be clear to you, this is a bijection because given any point, I can find a point on CD that corresponds to the given point on AB. And this relationship is unique because I can reverse it. If you give me point S, I can go like this to T prime and then combine it with P, obtain point T. Now, if you give me this point here, okay, combine it with P, okay, so this is the intersection and this is going to be the point that is mapped to this point. Okay, you see any point given on AB, it maps to a distinct point in CD, so this is really a bijection. It's a little bit confusing because we definitely have missing elements in CD. Nonetheless, we are able to find a bijection between the two. You see, What this entails is, cardinality-wise, the set of points on AB and the set of points on CD, they are equal.